Hi there, and welcome to a quick tutorial on approximating a binomial using the normal distribution. In this little video, I want to go over the conditions under which it's appropriate to approximate a binomial using the normal, and also show an example. Watch the video, take notes as you need to, and when you finish, come back and ask me about anything that's not clear. Okay, in fact, you don't even need to wait until the end of the video. Just come and ask me when you're stuck, okay, or if there's something you want to go over. We did do some of this before the half term, so hopefully this should be fairly clear. But if there's something that you didn't recognize or don't remember, come and ask. I'm going to put some notes up first. So let's consider the random variable x, where x is a discrete random variable, and it can be modelled as a binomial with n tests and a probability of success of p. It can be difficult under certain circumstances to calculate the probabilities. So sometimes we can use the normal to make an approximation. For that to work, the following has to be true. So firstly, n must be large. By large, we mean probably over 50, but because this is an A-level exam, if they ask you to do an approximation, then n is large enough. The question will often be, what are the two things that you need to, or what are the conditions under which you can use an approximation? And it must be that n is large and p is close to 0.5. Okay, so those are the two conditions. N must be large, and usually we'd say around 50 or more. P has to be close to 0.5. That's really subjective. I mean, I'd imagine something between 0.3 and 0.7. But again, if the question asks you to do an approximation, you can assume it's large enough. Now, if that's the case, then x can be approximated to a new distribution y, which is normal, with a mean of mu and a standard deviation of sigma. But we need to have mu must be equal to, sigma has to equal NP, so that's the number of trials times by the probability of success, and the variance, sigma squared, is N times P times 1 minus P. Or to put that another way, sigma, the standard deviation, is the square root of that. Now those conditions must be met in order for us to be able to approximate a random variable, which is binomial, as a normal distribution. So these are the notes that you need so far. You can hit pause and copy them down if you need to. Why is that? Okay, so if we have a binomial distribution, it needs to be symmetrical. Let me just try and sketch a binomial. So for this one, I've got a large n, and p is 0.5. It's roughly symmetrical. It looks a bit like the normal distribution. The normal distribution, of course, goes like that. So you can see that that looks fairly close to it. But this time I've got a smaller value of p, and this time you can see that it doesn't look like a normal distribution. It's not symmetrical, and so the approximation would be bad. If p is small. If p is large, too big, it looks the same thing but skewed the other way. The reason we need n to be large is so that it's big enough to eliminate the randomness, so we don't get, like, if you just roll the dice 6 times, for example, you might get 3 5s, and it won't be fairly spread. If you only do 2 coin flips, you might get both heads. It won't follow the normal distribution until you do a larger value of n. Okay, hopefully that gives you an idea of why we need it to be n has to be large and p has to be close to 0.5. Let's have a little go at an example. I'm going to go straight into a tricky one. Okay, so let's review this question. We are asked to do some work on this. A manufacturer produces large quantities of coloured mugs. It's known from previous records that 6% of the production are green. A random sample of 10 mugs is taken from the production line. Define a suitable distribution for the mugs in this sample. Find the probability that exactly 3 mugs were green. Okay, so to do this, I'm going to say, for part A, that let's call x number of green mugs, and x can be defined or can be modelled as a binomial. They're green or they're not green, where there are 10 tests and a probability of success of 0.06. 1 mark. Well done us. Okay, and now we're asked to find the probability that there are exactly 3 green mugs, so the probability that x equals 3. We can use the calculator to do that quickly. We're going to go to binomial PD because we want exactly 3. We're going to set n is 10. The probability of success P is 0.06. We want the x value to be 3, and if you do that, you get 0.0168. Okay, cool. Now we have a totally different question, so underline that bit. We're now changing to a random sample of 125 mugs. I'm going to use a different letter. Y is the number of green mugs in the sample of 125. So we can model then y as a binomial with parameters of 125 and 0.06 again. It says use a suitable approximation to find that they were between 10 and 13 inclusive. So we're looking for the probability that y is between 10 and 13 inclusive. We're told to use the normal approximation, so that's what I'm going to do. I'm going to let y be approximately the same as a model A. I've chosen A because Z's already taken. I can't, and I don't want to use B or N or any of those because they mean something else. Where A, so y is approximately the same as A, which can be modelled as a normal distribution with parameters of mu is going to be 125 times 0.06, which are 7.5, and sigma squared will be 7.05 because we just times that by 0.96. Okay, so we want the probability that A is between. Now, we have to make a correction here because 10 is a discrete value and we have to allow all numbers which would round up to 10. And we want to go up to 13. We need to allow for all numbers which would go up to 13. This is called a continuity correction. We're going from the discrete values for the binomial here to the continuous values for the normal distribution here. So when we're thinking about the values to put here, okay, you need to consider, like the number line, is this 10 rounding from 9.5 or rounding from 10.5? We want to make sure that it, in this case, to make sure that it includes the 10, so we need to go down to 9.5. We want to include the 13, so we go up to 13.5. Just think carefully about what the values are. Now this we can do on the calculator straight away. We can just type in the values and get an answer using the normal CD, always the normal CD. So the lower value will be 9.5, the upper value will be 13.5. Sigma will be the square root of 7.05, and the mu will be 7.5. If you go through all of those steps, you should get 0.2147, I hope. All right, so the big thing to notice here is the continuity correction that comes in it as well. Okay, slightly more straightforward example this time. I've got the binomial variable, the binomial random variable, the discrete random variable x is modelled using y. So find the probability that x is less than 50. I wanted to just do this to concentrate on finding the continuity corrections. So let's look at the first one, part A. We want the probability that x is less than or equal to 70. So let's think about that on a number line. We would see 70 is here. We want everything that's lower than that and including the 70. So it must be 70.5 because that would be the only way to include it. If we did 69.5, it wouldn't include the 70. That would be no good. So this is equal to the probability that y, the normal distribution, is less than or equal to 70.5. And then you can just use the calculator to type those in, and that is 0.4032. Okay, so I've used the calculator in normal mode, normal CD. I've had 0 as the bottom end, 70.5 as the top end, and these values put into the calculator top and as the mu and the standard deviation. All right, next bit asks for the probability that 80 is less than or equal to x is less than 90. All right, so we need to think how that would work with the y values. So again, I like to think of the number line. I need to have x between 80 and 90. I need to include the 80, but not the 90. So the line would go from here to here. So from 79.5 to include the 80, up to 89.5. Okay, so I'm going to go from, what did I say, 79.5 up to 89.5. Probably shouldn't have drawn the things in first. Okay, and so again, using the calculator, we can get that and find that it's 0.1081, I think. That's what I got anyway. So just using the top and bottom values, that's what I got. Okay, we've got time for one last example. We've got time for as many examples as I want, but I would like to do one last example. This is example 13 from your textbook. It's on page 54. So if you want to try it by yourself and then review my method, then that would be fine. Okay, so you might like to just go and do it by yourself first. Here, I'll bring it up. Okay, so we have a particular type of flower which has 55% yellow flowers. A random sample of 80 is planted. Now, is this appropriate for us to take as a normal? Well, let's look at the values. We have 0.55 as the probability, so that's close enough to 0.5 for us to accept. And n is 80, which is again large enough for us to take, so we can do this. It's a binomial that we can approximate as a normal. So I'm going to start by saying x is the number of yellow flowers, and x can be can be modeled as a binomial with parameters of 80 and 0.55. Okay, that's lovely to start with. Well, now we can approximate this using, we need to assign it another letter. I'm going to call it y, and y is an approximation of x, where y can be modeled as a normal distribution with our parameters mu and sigma squared. But mu will equal 80 times 0.55. 80 times 0.55, definitely a number. 44. And sigma, I'm going to put sigma squared. We need to remember that that's the variance and not the standard deviation. Is 80 times 0.55 times 1 minus 0.55. Okay, and that, again, calculator time, that's 19.8. So y can be modelled as a normal with a mean of 44 and a variance of 19.8. We're asked to find the probability that there's exactly 50 flowers. So the probability that x equals 50 is approximately the same as the probability that, okay, we need to do some continuity correcting here. So exactly 50 on the discrete values, that means that the y value must be between 49.5 and 50.5. Notice just here I've used strictly less thans. You can use less than or equals, it doesn't actually make a difference, but of course we know that the value of exactly 49.5 is 0. That's kind of the whole reason why we were doing this. So now I'm going to use the calculator to find that, and I get the value off the calculator using that as the lower value and that as the upper value. Typing it in, I get 0.0362. So 0.0362 was the answer that I've just got. If we go back, it says calculate the percentage error. So in order to do that, I need to know what the probability that x equals 50 is, and we can do that easy enough on the calculator. The probability that x equals 50 is 0.0365. We just need to type in using the binomial PD and the value 50, n is 80, and the probability was 0.55. We do that and it comes out as 0.0365. We now want the percentage error. So that's 0.0365 minus 0.0362, all divided by the original value, and then times by 100. I get 0.82% on my calculator. All right, hopefully that makes sense. Now, do remember to come back and ask anything that you need to, but let's review the main points. If we have a binomial, such as this one here, where x can be modelled as a binomial with parameters n and p, providing n is large and p is close to 0.5, we can use an approximation where we convert x to y, where y is modelled as a normal with parameters mu and sigma squared, where mu is equal to np and sigma squared is n times p times 1 minus p. And you must remember to apply a continuity correction. Okay, good.